Galileo Galilei was born on February 15th in 1564 in Pisa, Italy, and died in 1642. He was the oldest among 6 children of Father Vincenzo Galilei, a musician, and Mother Giulia degli Amanati. His family was not considered rich despite belonging to a noble blood. In 1570s, they moved to Florence. Galileo was an Italian polymath who made essential contributions to the knowledge of physics, mathematics, astronomy, and philosophy. His analysis of inertia, parabolic trajectories, and law of falling bodies made a great input in the study of motion. He also invented a telescope, which caused a major change in astronomy and advocacy of a heliocentric universe. However, it caused him to gain opposition from Catholic Church leaders and his further inquisition. His studies of pendulum began in the University of Pisa, where his father wished for him to study medicine. As the legend says, Galileo watched a suspended lamp swing back and forth in the Cathedral of Pisa. Only in 1602 he claimed his famous pendulum discovery, stating that the period of a pendulum, which is the time it takes for it to swing there and back, is independent of the arc of the swing, known as isochronism. Due to this finding, Galileo was inspired to continue his studies of pendulum and develop ideas of a pendulum clock. As for his personal life, Galileo never got married, although after meeting Maria Gamba in Venice, she and Galileo lived together in Padua and had 3 children. Later, Galileo moved to Florence, where his son joined him as Maria married someone else.
In his pendulum experiment, Galileo supposedly used 2 pendulums at the same time to compare them. The oscillations of each pendulum were counted and then compared. In our experiment, a water clock was used to measure time. A plastic bucket with a 1/4 inch hole connecting a plastic tube was filled with water. A team member used his or her finger to open the bottom outlet of the tube when another counted 10 oscillations of a pendulum. The mass of water collected in a flask was the unit of time measurement in grams. In each experiment, we changed our singular variable, be it weight, length of string, or angle of release. We did 3 different sets of experiments. First, we compared the period to change in length. You will see how we changed the length in the pendulum. Secondly, we compared that rate to a different mass.
You need help like opening it? Nah, you don't really need to open it.
Thirdly, we compared the rate of change in period versus length to a different amplitude. In the video, we switched from testing a 10-degree angle to 5 degrees.
9, 10.
Our pendulum's body was made from PVC pipe, as it allowed for easy construction. For a string of various lengths, we used yarn. Our weighted bobs were a golf ball and a tennis ball. The bobs are attached to the string by hot glue. The bobs were weighed after the strings were attached, so as not to compromise the weight values. The strings of the bobs are attached to the pendulum by a glasses case, acting as a large clamp. The clamp is attached by tape.
Theory. We expected the following from our experiments, as stated in the Galileo website. The pendulum experiment shows that the period is proportional to the square of the length of the pendulum. So as you take ratios of the period, that should be very close or similar to the square root of the ratio of the length. Further, Bob's race to different heights at the start of the experiment take the same time, or nearly so, to complete one cycle, thus proving the period is independent of amplitude. The fact that blobs made of different densities have the same periods shows that they have constant acceleration, which contradicts Aristotle's claim that objects of different weights fall at different speeds. Relationship between L and T. Torque equals inertia times angular acceleration, which also equals negative angular momentum times Fg sine of theta. For small angles, we can replace sine of theta with just theta, and in turn, angular acceleration equals negative mgl over I theta. Therefore, omega squared equals negative mgl over I, and I, moment of inertia, equals ml squared for rods, and angular velocity squared equals mgl over ml squared, so the m's cancel and an l cancels, so we're left with omega squared equals g over l, and omega equals the square root of g over l. And the period t equals 2 pi over omega, which is 2 pi over the square root of g over l, or 2 pi times the square root of l over g, which is true for small angles.
Our data has shown that there is a direct correlation between the length of the pendulum and the time measured using the water clock. It is known that the period increases with increasing time. Thus, the collected data proves that the period is dependent on the length of the pendulum, as indicated by the graph with the time versus pendulum length. The data points tend to have a positive slope. This is because we increased the length of the pendulum, more time it took for the pendulum to complete 10 oscillations. This tendency fits the derived formula for calculating the period of the oscillation. In the second experiment, we used two different masses with the same change in length and same angle of release. Our data has shown that there is no correlation between the mass of the pendulum and the time measured. The collected data proves that the period is independent of the mass of the pendulum. This is indicated by comparing two time versus length graphs. The masses of the two pendulum in both graphs are different. However, the data points of each graph is nearly identical. As indicated by the two graphs, the data points tend to have a positive slope. This is because it took more time for the pendulum to complete 10 oscillations. As we increase the length of the pendulum, this tendency fits the derived formula for calculating the period of the oscillation. Theoretically, this is known as the period increasing with the time. For test 3, we used the angle of 10 degrees because we would not have been able to use any larger angles for the equation of the period. Our data has shown that there is a positive correlation between the amplitude of the pendulum and the time measured. This is indicated by comparing the two time versus length graphs. The amplitude of the two pendulums in both graphs are different. In the data points of the pendulum of the higher amplitude has a higher amount of time completing an oscillation. As indicated by the two graphs, the data points tend to have a positive slope. This is because it takes more time for the pendulum to complete 10 oscillations. As we increase the length of the pendulum, this tendency fits the derived formula for calculating the period of oscillation.
Length dependency. The first test included a tennis ball, 5-degree angle of release, and changing pendulum length. We measured the periods of 10 different lengths varying by 2 centimeters. The longest pendulum of 33 centimeters measured a period of 199.1 grams, while the fifth trial of 25 centimeters measured 170.21 grams. The ratio of these two measurements is equal to 0.8548. The square root of the ratio of their lengths is equal to 0.8703. The percent difference between the two is 0.631. Still using the longest pendulum with a period of 199.1 grams against the shortest length of 15 centimeters measuring 135.6 grams. The ratio gave us the number 0.681. The square root of the ratio of their lengths is 0.674. The percent difference between the two is 1.027, thus proving the theorem of the period is proportional to the square of the length of the pendulum. Mass dependency. Our second test included a tennis ball, golf ball, 5-degree angle of release, and changing pendulum length. We measured the periods of 10 different lengths varying by 2 centimeters. The changing variable was the mass, as we used 2 different balls. The measurements of the period for the golf ball came out very similar to the ones of the tennis ball. For the first trial of both tests, the discrepancy was 5.9% and observed to be the highest. The lowest discrepancy observed was 0.27% for the 8th trial of both tests. Galileo's discovery turned out to be very true for this experiment, thus proving the theorem: the period is independent of the object's mass. Angle dependency. In the third test, we had the same mass, 5 and 10 degree angles of release, and changing pendulum length. We measured the periods of 10 different lengths varying by 2 centimeters. The changing variable was the angle. The measurements of the period for the golf ball came out slightly similar to the ones of the tennis ball. For the first trial of both tests, the discrepancy was 14.6%. The lowest discrepancy observed was 10.2% for the 8th trial of both tests. The theory that the period is independent of the object's amplitude was not supported with our data. It shows a slight difference in the period as the angle changed.